The V2X Abstraction Layer provides a low-latency service layer fusing and aggregating information from different subsystems such as V2X Radio, ADAS Horizon, navigation, traffic services, and positioning. It enriches the data received via V2X Radio with information available in the vehicle system. Using filters, it makes them available to the registered applications, providing the driver with aggregated data and warnings that are more precise. The following filters are available and serve as an example: accessibility of an object on the horizon tree, speed, direction and distance, and historical path or present on the route. Applications can freely configure the required filters via a graphical user interface. By updating the filters asynchronously, the applications are notified immediately. The V2X Abstraction Layer can represent all cooperative awareness use cases transnationally and independent of the used radio technology. Hazard analyses are performed based on the available road network and learned or planned route. The system is designed to be fail-safe. In the event of lacking input information, the reliability index drops and gives the application the option to switch to fallback solutions, such as handling only so-called day one use cases. The V2X Abstraction Layer is equipped with universal interfaces, which allows the docking of solutions from other manufacturers, like another V2X network stack or ADAS or navigation system. The system also works for the Chinese market, whose coordinate system is distorted by algorithms. The system can currently process up to 800 objects simultaneously. For high-priority objects, a latency of less than 2 milliseconds is guaranteed by giving higher priority to objects with high speed and in the proximity to the host vehicle. The V2X Abstraction Layer is not only suitable for receiving V2X data, but also provides an interface for sending data. The authorizations are checked via service-specific permissions from the certificates, which makes them also usable for emergency vehicles. The concept also takes DLT logging with data analysis tools and data replay into account, making it fully compatible with the Tempo Justo workflow, as it is used for our OneCore Go navigation. This overview shows the main function blocks. The green area represents the V2X Abstraction Layer. All gray boxes are external to the V2X Abstraction Layer and can run on other computing units. For our software test, we choose two locations in our hometown, Hamburg. The first one is an intersection with a bridge crossing above it. The second one is a parallel road layout. For the simulation of V2X Abstraction Layer, we use the traffic simulator Sumo. It simulates city traffic on OpenStreetMap in a particular way, so we can reproduce the scenes at any time. Via the V2X interfaces, we supply the common awareness messages of the road users, as well as the position of the host vehicle into the system. An NDS library enables access to the road network. We visualize the results using Tempo Justo, our debug tool. This is the Sumo simulator. The traffic on the road starts to move. The V2X cam messages, which are emitted by each traffic participant, are fed into the V2X Abstraction Layer, as well as the position of the simulated host vehicle. This way, the unit is put under load on the input side. This chart gives a brief overview of the used markings. Blue lines mark the horizon build-up in front of the Ego car. The two circles mark the detection area for the horizon. The outer one marks the expansion in the direction of travel. The inner one marks the area behind the vehicle, which marks the spot of removal of the horizon. The vehicle in the center is the host vehicle. Green triangles mark vehicles which are relevant and part of the horizon. Gray triangles mark vehicles that are not part of the horizon. Each vehicle leaves a trace behind. The red dots mark the so-called dead reckoning position. The green dots, the map-matched position. This is what the simulation results look like. The group of vehicles crossing the bridge from the northwest have been digitally detected, but remain grey because they're not on the horizon of the ego vehicle. The vehicles coming from the north gradually turn to the green because they have been recognized as relevant to the horizon. As the route continues, you can see how the horizon behind the vehicle is reduced. In the parallel road scenario, it is also visible that the vehicles on the sideline are digitally recorded, but are classified as not relevant for the horizon. As soon as the vehicles turn from the sideline into the horizon area, their color changes to green. Finally, you can see the filters working. In this example, a total of 7 filters are predefined. Their status can be recognized with a tag on each vehicle. Examples are exceeding a defined speed limit, reference to the horizon, blind spot warning, and displaying of passing left or right. The next steps on our development road are refinement of the horizon expansion, the use of historical movement data from the V2X protocol, expansion of the application filters and selectors, object prioritization, and the creation of further test cases.